Hello, this is Ayush Vikram, and I'm going to present my project, the Naive Bayes Sentiment Classifier. So the objective of this project, right, the problem that we were trying to solve is to be able to develop a classifier to predict the sentiment of reviews, right, which are generated by users based on their experience with product or service, solely based on the words that are used in that review itself. We want to develop some sort of classifier to kind of predict the sentiment. And by sentiment, I mean either positive or negative. So there are only two possible sentiments based on the words that are used in the review. So how are we going to do that? What method are we going to use to create such a classifier? So the method I decided to use, or algorithm that I decided to use, is known as the naive Bayes classification algorithm. And the naive Bayes classification algorithm is related to Bayes' theorem for the calculation of conditional probabilities. Um, so as you can see here, this illustration, this illustration is essentially Bayes' theorem, and the objective of naive Bayes classification algorithm is to calculate this posterior probability for each class. So in our case, we have two classes. We have positive or negative, right? The sentiment. So we want to calculate this posterior probability for each class. And the posterior probability is given as P of C given X. So what is the C in X? What is the probability of C given X? So the C is the class, right? And X is quite simply the words that make up that review that we're trying to classify. So for each review that we want to classify as either positive or negative, we calculate this posterior probability, which is quite simply the probability of the class. So the class equals positive, right? Or class equals negative, given X. And X, as I stated, is quite simply the words that the review consists of, right? It is the words that are in that review that we're trying to classify. And we are trying to we're trying to classify these reviews solely based on the words that are in the review itself, right? So X is quite simply the words that are in the review. So we're trying to we're trying to calculate this probability of a class, of some class, either positive or negative, given X, given the words in the review. That is our main objective, and that is the posterior probability we're trying to calculate. Since in our example, we have two classes, we're going to have two posterior probabilities to calculate for each review. So to calculate the posterior probability, we need to calculate this thing known as the likelihood probability. So the likelihood probability, as you can see, is the probability of some of the X given C. And X, as I stated, is just the words that make up the review, that are in that review that we're trying to classify, just all of the words, right? And by words, it can mean unigrams, right, which are just single individual words. It can be bigrams, which are pairs of kind of consecutive words. It can be any other degree of n-grams as well, right? So that is what the likelihood probability is. It is the probability of these words, right, which can be either unigrams, bigrams, and so on, given C, given the class, right, either positive or negative. And we multiply this likelihood probability by the class prior probability of C. So the class prior probability is the probability of the class itself. So it's called prior because it's usually based on some sort of prior assumption or prior calculation, right? Because so let's say in our case, the two prior probabilities will be the probability of having a positive review and having a negative review. So to get these prior probabilities, we can use our data, training data, and see what proportion are positive or negative, or maybe we've done some searching online and on the product, right, that we're analyzing, and we know that usually 70% of reviews are positive, or there are many ways to get this prior probability. So going back to the likelihood probability, right, the p of X given C, and X being the words, right, in the review given the class. So thanks to an important assumption that naive Bayes makes, which is known as the assumption of conditional independence, this calculation of the likelihood probability can be simplified. So the conditional independence assumption means that we assume that every word in the review is conditionally independent with each other given the class. Okay, so this assumption of conditional independence basically means that the calculation of the likelihood probabilities is now just a product. You multiply these smaller likelihood probabilities, right? P of x1 given c times P of x2 given c all the way to P of xn given c. Now, what are these smaller likelihood probabilities? These are just the probability of a word given c, right? X1, let's say, if we're dealing with unigrams, it's the first individual word in the um, review. So probability of x1 given c is the probability of the first word given c. Probability of x2 given c would be the probability of the second word given c, and so on till xn. So this greatly simplifies the calculation of the likelihood probabilities, and this can be done thanks to naive Bayes' assumption of conditional independence among our words, right? And note that we are using the bag of words model or assumption as well. A review to us is simply just a bag of words. It consists of its constituent words. And by words, I mean either unigrams, single words, or bigrams, right? Groups of two consecutive words, or even a higher degree n-grams. So that we're using the bag of words models, and that means we are not considering the relative positioning of the words. We don't care if one word comes after another word. We are treating each word kind of almost independently of its order. And this is another powerful assumption that we are using, the bag of words assumption that greatly simplifies calculations. And so let's talk about this likelihood probability, right? So what is the definition of these likelihood probabilities? The likelihood probabilities, right? These individual likelihood probabilities I'm talking about now, P of x1 given c, P of x2 given c, all the way to P of xn given c, which you multiply to get the total likelihood probability for a review. Each of these smaller likelihood probabilities is quite simple. It is the count of the word, right? By word, I mean either unigram, bigram, or whatever your model entails, plus k. K is a constant known as the Laplace smoothing constant. I'll get to that in a second. Divided by n plus k times the number of words. So what is n words? N, this uppercase n, and this kind of magnitude of words. And what is k? Let's talk about that in our notebook, right? So the k is the Laplace smoothing parameter or constant, as I mentioned. And the Laplace smoothing is used to ensure that a word does not have a zero likelihood probability, right? Even if we've never seen that word before in our training stage, in our training data set, that does not mean that word cannot be present in a review in the test data set, right? So just because we haven't seen a word before in training data set and it appears in the test data set does not mean we assign it a probability of zero likelihood, because I think that's irresponsible. That a zero probability means that it has kind of no chance of appearing, which is not true, right? Kind of a never before seen word has a small probability of occurring. So we add this we kind of add this k, the constant, just to ensure that unseen words in the training phase don't have a zero probability in the testing kind of phase. And so the likelihood probabilities is quite simple. It's the count of the word plus k, this Laplace smoothing constant. I used one throughout the project, divided by the capital N plus k times its magnitude of words. So k is the Laplace smoothing parameter. As I said, I've just used one. N is the number of words in reviews of that class. So as I stated before, the likelihood probabilities are conditional upon the class, right? They're a probability of the word given the class. So given that, so whatever that class is, n is the number of words in all reviews of that class in the training set. And this kind of magnitude of words, or magnitude of X, you can call it, is the number of unique words in both classes. So essentially, it's the number of unique words in all reviews of the training set, right? And that is how the likelihood probabilities are calculated. And as I stated before, thanks to the assumption of conditional independence, we multiply these likelihood probabilities for each word in our review, and that's plays a major part in the calculation of the posterior probability. So let's talk about how. So let's go continue talking about naive Bayes, the naive Bayes model, and let's consider. So after we let's note the fact that the likelihood probabilities are calculated during the training phase. This is very important. So they're calculated in the training phase, not the testing phase. The testing phase is when we're trying to classify each review, and that's when we calculate the posterior probabilities, right? So in the and we already have, when we calculate the posterior probability, we have these likelihood probabilities from our training phase, and we can just kind of take the product and multiply with the prior probability, which we also have from beforehand, and then we get the posterior probability, right? So as I stated before, in our case, since we have two classes, we have two posterior probabilities. So a um, how do we classify a review as either positive or negative? Well, we take the maximum. It's quite simple, right? We take the maximum of either the positive posterior probability, which is just the positive prior probability times the um, likelihood probability given the class is positive, times or the negative posterior probability, which is the prior negative probability times the posterior likelihood probability given the class is negative. So we take the maximum, right, of the two posterior probabilities, whatever it is, and whatever is the maximum, we assign that to be the uh, classification, right? So if the positive has a greater posterior probability, the review is classified as being positive. So quite simply, naive Bayes works like this. The posterior probability is equivalent to the prior probability times your likelihood probability and divided by the denominator, right, which comes from Bayes' theorem. However, note that when we're trying to maximize this posterior probability, we don't need this denominator. We just need to maximize this numerator, right? So this posterior probability is proportional to just the product of our likelihood probabilities, which we can take the product of individuals set separately, thanks to the assumption of conditional independence, with the prior probability. And we don't even need to consider the denominator. So that's an important point when models and classifiers are constructed using the naive Bayes model approach. So that is a brief overview of how naive Bayes works. And let's consider the fact, why did I choose a naive Bayes as the model or algorithm of choice in constructing this classifier? Because there are other ways to construct classifiers, right? There are a lot of ways. So why did I choose naive Bayes? Well, naive Bayes is quite simple to train, actually, especially in a supervised learning context when the data is already labeled. And our data is already labeled. I will get to the data in a second, but it has a score, right? The reviews come with a numerical score that can easily be turned into our label. So that makes naive Bayes an attractive choice. Also, naive Bayes is kind of simple to train, and it's simple mathematically thanks to its numerous assumptions. We're making assumptions like the conditional independence assumption, where we can just simply multiply the kind of likelihood probabilities of each word together. That's an assumption of naive Bayes. We're using the bag of words model, where each review just consists of its words. We're not considering the ordering of the words or anything like that, just considering the constituent words. That's another assumption that simplifies calculations. So we can do a lot of powerful things with naive Bayes, despite the fact that it's quite simple and has these kind of assumptions that simplify calculations. In fact, in the real world, naive Bayes is considered to be one of the more accurate classifier algorithms, and it has achieved high class accuracy in many cases, despite being so simple. And it is also efficient. It's more efficient than the majority of classification algorithms out there. I believe it is somewhat close to linear time, so that is another factor as well. So let's talk about the data. The data is from Kaggle, and it is a data set from Kaggle. It's open source. It was downloaded into Google Drive and imported into the notebook using the pandas data frame read as a pandas data frame using the read CSV function of the pandas module. So it has three columns: the ID column, which is simply each row has its own unique ID, right? And the review, the second column, is the actual string, right? It is the review and the score. So each review is associated with a numerical score ranging from 1 to 5. So these three columns make up kind of one row, and there are 107,018 rows total of data. So it is a vast data set. And we originally split it into two, right? We split it into the training set and test set halfway evenly of 53,509 rows or tokens each. So that was the initial split, right? That was a simple split done. But the issue with that split is that with splitting it just halfway is that among the training and test data sets, the proportion of reviews that are, when we consider the proportion of reviews that are either positive or negative, we see that positive reviews there are such a higher proportion of positive reviews than negative reviews. 90.5829% of reviews in the training data set are positive, compared with only approximately 9% negative. Same story in the test data set: 91.1193% positive reviews and 8.8807% negative reviews, right? And you might be asking, well, why is this an issue, right? So the issue comes because when we use our naive Bayes model, when we use our model, let me also mention that as I've mentioned before, the words can be either unigrams or bigrams. So I decided to create two classifiers, one based solely on unigrams or individual words, and the other based on bigrams, which are groups of two words that appear consecutively in a string, right? So, and my hypothesis for also doing a bigram classifier was that there are certain groupings of two consecutive words that do appear when a language with a particular sentiment associated with it is written, like good job and things like that, right? And with using bigrams, we do get that order. We do get somewhat of an order association, right? So let's say someone writes, "Oh, this was not good." If you're doing unigrams, you might see the good, and that might affect. Even though this is a negative review, we might be inclined to maybe have a higher chance of classifying it as a positive review, right? But with the not good, that would be accounted for with the bigram model. We might be able to better handle these type of cases, right, with these kind of outlier singular words. That was my hypothesis. So the reason why this is an issue is that when we use our naive Bayes model, the unigram and the bigram, on the training, when we train it and test it on the data set, the accuracy that is received is 91% for both, around 91% for both, 91.6% for the unigram, and 91.9% for the bigram, using this kind of original data set. This is split halfway down. And so look, the accuracies, I was alarmed at this. These accuracies are too close to the proportion of the training and the test data sets, especially the test data set, that are positive reviews, right? So basically, if you go into the test data set And if you just assign if your model just assigns every review as a positive review, right? Then you're going to get a 91.1% accuracy, which is close to what we're getting with our model. So I wanted to verify if our model actually works. And to do that, we needed to kind of change up the data. We needed to make the data more even, less skewed than this, not perfectly 50-50 proportion of positive and negative, but more even. So we wrote a function that's in the notebook, and this was the new proportion, right? This is kind of our new or fair balanced training data set. We see that 44.57% of reviews are now positive and 55.42 are negative. Similar ratio, close in the new test data set, and the similar value for negative reviews as well. So now you can see that there's this sort of skew or dominance of one class is not there, and we can now hopefully verify our model by getting a high accuracy, a relatively high accuracy, um, and it'll we won't have doubts that, oh, we're just simply guessing and selecting one class for everything and getting that accuracy. So again, as I mentioned before, when we work with our original or kind of the unbalanced, imbalanced data set, we get a kind of accuracy of 91.63, 66% for the unigram and 91.9% for the bigram, which may sound good initially, but when we consider the fact that 91% of tokens were positive reviews, it calls into question, well, what if someone just what if the model is trained, it has been overfitted on the training data set and is almost calling positive for everything, right? So to kind of validate the model, I decided to create have this new data set, right? The new test and training data set where the kind of proportions were a little bit more balanced, but not exactly. And for this new data set, the accuracy for the unigram was 83.6582% in classifying the test data set, and the the bigram accuracy was 80.54%. So and the so these test and training data sets were not 53,000 entries. They were around 9,000 each. But we see that, okay, this is a promising sign, right? Because even though, right, these accuracies are lower than before, but we have to consider the fact that this is a promising sign because our accuracy of 80 to 83% is higher than these individual proportions. So this indicates or kind of strongly suggests that the naive Bayes our models that we've created, our classifiers, are actually learning from the training and test data sets, and they're not just simply guessing all negatives or all positives or something like that, right? So they are learning, and they are attempting to learn learn and learn from the training data sets and classify the test data set accordingly. So this is a promising sign for our initial problem statement of calculating the sentiment of reviews using the naive Bayes bag of words model, right? I think this was a promising sign. And so based on the errors, right, I wanted to see, considering the errors, what type of errors are they? They're false negatives, right? Which is or false positives. False positive is when some kind of something in actuality is negative, but it's calculated as a positive, and false negative is vice versa. So I wanted to see what the make up the errors were when we use the original data set, right? The one with the 90% positive. Um, the and we use our unigram model, we get around kind of a 41% false positive rate, 58% false negative rate. And when the bigram model is used with the original kind of data set with the 91% positive, we get a more balanced kind of error rate. we get a 48.77% false positive rate and 51.2% false negative rate. This is a more even rate than the unigram model with the original data set. And I guess this means that if your data is if your data that you're dealing with is like the original data set, right, where one class is makes up a tremendous proportion of the total data training and test data sets, then and if you want the kind of error ratio to be even, then you might go with the bigram model. The bigram model also had a slightly higher accuracy, 0.3% higher accuracy, which is very minor. You might go with the bigram accuracy. If you wanted to minimize false positives, right, and you had a similar data situation to the original data set where one kind of class was a huge proportion of the total data, and you wanted to minimize false positives, right? Let's say it's okay in your specific application, depends on the application, right? It's okay to let things go undetected, but false positives raise a lot of huckus and disruption, and they raise a lot of kind of activity. Then maybe it's okay. Then maybe you wanted to minimize the chance of false positive, the rates of false positives, and then you might go with the unigram model. It depends on your application for sure. And the interesting thing is the distribution of errors for the unigram model with the new data set, right, with had a 44% to like 55%, right, kind of split between positive and negative. False negatives were the overwhelming majority. There were 97% in the unigram model, which is interesting. So false negative is when something is classified as negative when it is actually a positive, right? When in actuality is a positive. So most of the errors were things that were actually positive being classified as negative. And that's an interesting occurrence. Maybe it has something to do with the fact that there were more negatives this time, slightly more negatives, right? The proportion of negatives was higher, but this is interesting to see the overwhelming false negative rate. Same thing with the bigram model of the new and balanced data set. It had an overwhelmingly false negative rate. So if you're in an application or field where you have your data looks similar to the kind of the balanced new data set that I created, where the proportions are kind of roughly similar, but then and if you want to minimize the chance of false positives, then either the bigram or the unigram model would be a good way to go. And as you saw, the bigram model actually had a kind of lower probability, a lower accuracy of around 3%. That's significant. That does not support my initial hypothesis, right? That the bigram, maybe having a bigram would increase, a bigram classifier would increase accuracy because we're kind of reducing the influence of these kind of outlier individual words. But and I wonder a future exploration and a continuation of this project could be to see if that hypothesis holds up with other training data sets, or maybe even extending it towards um, higher degree of n-grams, not just bigrams, trigrams, 4 grams, and so on. So let's talk about the some I guess future plans or future considerations and some issues with the project. So let's talk about that. So one, I think, future consideration is that we can combine our unigram and bigram models, right, into what's known as a mixed model. So the posterior probabilities in the mixed model are simply essentially a sum of the posterior probabilities for the unigram and bigram models, right? And they may be weighted by some factor, but they're essentially a combination of these posterior probabilities. And we should explore a mixture model so we're getting the benefits of a unigram analysis and a bigram analysis. This would be something interesting to explore in the future. And something else that would be interesting to explore would be expanding the model to higher degrees of n-grams, as I mentioned previously, just trigrams, 4 grams, etc. And maybe we combine those in a kind of a large mixture model with unigrams and bigrams and see what happens. So mixture model is the combination of a unigram and bigram model instead of handling those separately into one model where the posterior probability is essentially a combination
of these kind of individual posterior probabilities for unigram and bigram. Um, so an issue definitely with the data that we had is and this kind of speaks to the quality of the data, right? And is the potential prevalence of typos and other maybe grammatical mistakes, typos, and some sort of weird characters which can affect the accuracy of the model. So in the data cleaning stage, we I removed all punctuation characters, and I did make everything lowercase. I replaced punctuation with space, but there might be some weird characters, and there might be typos. So typos is very can definitely affect the accuracy of the model, because of the classifier. Because a typo means that that word will not be recognized, right? It won't be recognized when that word comes up in your, for example, in your training stage. It'll affect the likelihood probability of that word. It's going to be the typoed word, the mistyped word will be classified as a never before seen word, so it'll have a likelihood probability of close to zero, which will mess up the kind of the when we're calculating the posterior probabilities. It'll affect the posterior probability, and that will affect the classification of that review in the test stage. So typos will it impact the posterior, the likelihood and the posterior probabilities, and potentially the accuracy of the model itself, because we have no way of knowing that a mistyped word is truly in fact another word. It'll be classified as a new word, which provides issues in training and test stages. It'll have a kind of a likelihood probability of close to zero. Um, so another issue is that I use the split function to separate words, right? From string, the string into words. So the split works on kind of spaces and new lines and things like that. So a user might forget to put spaces between words, let's say. So, and since words are split by spaces and new lines and data preparation stages, each string is split by spaces essentially, since there weren't any new lines. This word might not be an actual word in the English language. Well, perhaps it'll be a combination of many individual words, right? Since the user forgot to put a space, which is a common error when typing, especially informally in reviews. So this is definitely going to harm the accuracy, similar to the typo, because it's going to affect the calculation of likelihood probabilities, um, and it's going to affect the frequency, right? Which the likelihood probability calculation depends on the frequency. It's going to affect the frequency of multiple words, all of the words that are possibly uh, kind of part of that large word. Those frequencies will be impacted, and thus the likelihood probabilities will be impacted, and then the posterior probability and the accuracy of the model will be impacted. So when dealing with kind of data created by humans, it's important to keep these kind of data quality considerations in mind, and it's important to debate whether it's worthwhile to create some sort of algorithm to maybe resolve, maybe we're using some sort of Hamming distance, perhaps, right? Going through words, and if it's a distance of one um, from another word, maybe we count those as the same word, maybe using maybe considering the lemmas of each word, right? We learned about lemmaization in this class. So those are important things that definitely need to be explored in the future and with similar projects. Um, so again, I just want to reiterate that naive Bayes is a really good methodology for developing probabilistic classifiers. It's kind of simple, it's efficient to train, as you can see in the project. It wasn't too mathematically intense, especially when the data is already labeled. And it's made easy due to its several assumptions of kind of conditional independence, and even our bag of words assumption simplified calculations quite a bit. But nevertheless, naive Bayes performs quite well in real world situations. So as an easy method of classifying labeled data, and is a efficient one as well. So that's why I think it's attractive to many people who are trying to solve classification problems today. And I think all in all, our model was successful. I think it is promising, right? It's not. I don't think it's at a kind of perfect stage yet, but it was promising. It showed around 80% accuracies for our balanced data set when we had a smaller data set, but it was more the proportions of positive and negative reviews were closer to 50-50, not exactly around 45 and 55% uh, positive and negative. Um, So that was around 80%, 83%, and that indicates that the model is learning, right? It's not just guessing one or the other, because then we would see, if it was guessing, we would see a accuracy of around 50%, right? It's halfway, but it's not guessing one and the other. We're not getting a accuracy of that is equivalent to one of the proportions, right? And we did this. We had to do this because we wanted to verify our model, because the the issue with the original data is that it had a lot of positive calls, right? 91% of proportion of positive calls that dominated the total data, and this called into question our model, because you can just simply guess positive in that scenario. So we wanted to verify our model, and I think that the new data set, the kind of balanced data set, and these accuracy values do validate that this is a promising approach, and they do support our initial problem statement, which is whether can we solve this kind of, or kind of solve this, or develop a classifier which can kind of develop predict the sentiment of a review, but just based on the words that are in the review. And we wanted to do this with a naive based classifier, and I think this is a promising and fruitful result. And I think this worth warrants further exploration and study, and this is something I'll be gladly happy to continue learning about as I continue my kind of education in the future. Thank you, and that's all I have to say.